Today we're going to talk about momentum a little bit further. We introduced the concept of momentum and impulse, and now we're going to look at applications in terms of conservation of momentum and using conservation of momentum to look at certain types of collisions. So just remember, last class we looked at momentum, right? Momentum is defined as the mass times the velocity. So momentum is a vector that points in the same direction of the velocity. And we were able to rewrite Newton's second law in terms of change in momentum with respect to time. So force acting on something causes a change in momentum with respect to time. And an amount of change in momentum we defined as the impulse. Another way to write the impulse is for a constant force over a certain amount of time. It's the net force times the change in time. So I'd like to look at a particular situation here where you have two balls colliding. Ball 1 and ball 2 collide with each other, and this graph shows the force they interact with each other while they're colliding. So during the collision, the force gets stronger and stronger, and then they move away from each other, and then the collision ends. And so there's a force of 1 on 2 that way, and a force of 2 on 1 that way. And Newton's third law, for every action is an equal and opposite reaction, says that the force of 2 on 1 is equal to minus the force of 1 on 2. So if I apply Newton's second law, right, that force is equal to dp dt, I apply it to each of those, I can say that the force on 1 is equal to d momentum of 1 dt is going to be equal to minus d momentum of 2 dt. And then next I can say, well, let's move everything to one side. So let's move both terms to the left side of the equation, and then multiply out the dt on the bottom. So I have dp1 plus dp2 equals 0, and I'm going to integrate both sides of that. And when I do that integral, basically integral of dp is just going to be the p vector, and the integral of dp2 is going to be the p vector, and there's going to be a constant of integration, which we'll move over there and we'll just call it a constant. So this is an interesting statement. This says that the total momentum, if you add the momentum for 1 and the momentum for 2, it's a constant at any time. During the collision, before the collision, after the collision. This is saying that the momentum, the total momentum of the system is conserved during the collision. And we can use this to solve all kinds of problems. Here's an example of, three billiard balls colliding. They have all this complicated interactions. One exerts on 2, 2 on 3, 3 on 1. They all exert forces on each other, but the total momentum before the collision should be equal to the total momentum after the collision. Here's an example of conservation of momentum, right? If I have a rocket just sitting there, it's a rocket with a bunch of fuel and it's at rest. One way to think about conservation of momentum is the rocket then begins to emit some fuel that way with a certain speed. And because it's emitting fuel with a certain momentum that way, in order for the total momentum to stay 0, it has to gain momentum forward. So the sum of the momentum of all the fuel plus the momentum of the rocket should add up to 0. And that's basically how you can sort of use conservation momentum to understand how rockets work. And we're going to look at that in more detail a little bit later on. But I want to look at a specific example here. So this is man and a child. They are at rest and they push on each other. And after they push on each other, and they're on ice, they're wearing ice skates, they're on ice, and so there's no friction to worry about. And after they push on each other, the man is moving at 1 meter per second to the left, or we say its velocity of the man, b, is minus 1 meter per second. So let's write down everything we know real quick. So the mass of the child is 50 kilograms, right? The mass of the man is 80 kilograms. And the velocity of the man after the collision, or after they push off each other, is minus 1 meter per second. And they both start at rest. And it's asking us to find what is the speed of the child after. Well, we can use conservation of momentum to do this, right? Conservation of momentum, remember the equation is just that the total momentum is a constant. So one way to write it is the total momentum initial is equal to the total momentum after. All right? Now the total momentum initial here is, if you look at this, the man and the child, they're both at rest, so there's neither of them are moving, so the total momentum initial is going to be 0. Now the total momentum after is going to be the mass of the child times the velocity of the child plus the mass of the man times the velocity of the man. And so we want to find how fast the child is moving. So let's solve for VA. So VA, if I move things around, is going to be equal to minus the mass of the man divided by the mass of the child times the velocity of the man. Let's plug in everything here. So it's minus 80 kilograms divided by 50 kilograms, and the speed of the velocity of the man was minus 1 meter per second. So if I plug in everything, you notice the two minus signs cancel. We end up with plus 1.6 meters per second. Does that make sense? If we look here, so they're both at rest to begin with. At the end, the man is moving 1 meter per second that way, and the child is moving 1.6 meters per second in the opposite direction. If you do 1.6 times 50, that's going to be equal to 1 times 80. And so they'll have equal and opposite momentums, adding up to a total momentum of 0. Well, let's talk about the different types of collisions that we can investigate. So the elastic collision is one where the momentum is conserved. We're going to assume that momentum is always conserved, and the total kinetic energy is unchanged or conserved. So the total kinetic energy of the objects before the collision is equal to the total kinetic energy after. It's a very good approximation for a lot of common situations. Usually some energy is actually lost during that. So most collisions are actually inelastic, like some energy is lost in deforming the object or making noise or friction or all kinds of things. But you know, if I tell you it's an elastic collision, you can treat it, you can use the elastic collision results. Most collisions are actually more inelastic, and a completely inelastic collision is where the two objects stick together, and that turns out to be the most loss of kinetic energy. So we'll end up looking at the situation where it's a completely inelastic collision first. So here's an example of here's the idea between a completely inelastic collision. So I've set up this here so that it'll show you when the two objects stick together. So if I hit play here, you see that after the objects collide, they stick together and they move together as one piece. That's like if you have something stuck to the other. In this example here, right, a moving glider is moving along, and then it sort of connects with this thing, and they move together with a common speed afterwards. So that's one type of collision. Now, we can develop a simple equation for that. If I have here, if you look here, we have V1 initial, we'll drop that X for this moving object, and we're going to assume that the second object or the target is at rest to begin with. That makes it easier. Then after the collision, they're going to move together with a final common speed, which we'll call capital V, which is their V final. So we say P, the initial momentum, is going to be equal to the final momentum. So the initial momentum will be the mass of 1 times the initial speed of 1 plus the mass of 2 times the initial speed of 2. That's going to be equal to the mass of the final thing. And the final thing, they're stuck together. So it's going to be m1 plus m2 times capital V. And as I said, this one is initially at rest. So we have an equation that relates V1 equals m1 plus m2 v. So this equation here describes, we can use it to find the final velocity of an object after a collision. And so here it is, this is sort of the generic setup, right, where they're both moving. Then afterwards they're moving to get, this is like a generic collision, but this is a collision where they completely stick together. So mass 1 comes in, mass 2 is initially at rest, and then they move together as one. We'll look at more general ones later, but this is sort of the first example that we did. And here's an example. We have a 3,470 kilogram truck going at 11 meters per second, and it runs into a stopped car, but they stick together. Let's say the bumpers get caught together and they keep moving afterwards. So how fast are they moving just after the collision, ignoring friction and things like that with the ground? So we can do this. Let's start by writing down everything we know. I always like starting by writing down everything we know. So let's see. First thing we know is that M1 is 3,470 kilograms. We know that the initial speed of the truck is 11 meters per second. We know that the mass of the car is 975 kilograms, and we know that the initial speed of the car is 0. And we're trying to find the final speed. And the equation we're going to use, right, is this equation, this very specific equation that's only for perfectly inelastic collisions. So it's m1 v1 initial times m1 plus m2 times this capital V final, right, or v. So let's solve it for v. So v is just going to be m1 v1 initial over m1 plus m2. So it'll be moving at 8.5, plug in all those numbers, 8.5 meters per second. Okay, so after the collision, the two things moving together will be moving slightly slower. That's kind of what we expect here. For this problem, we have two objects approaching each other and they're both moving. This is different, right? We have an air track glider with mass 0.15 and it's moving to the right at 0.352 meters per second, and then the other one is moving to the left with 0.447 meters per second, so it's written as minus 0.447 meters per second and has that mass. And they collide perfectly inelastically, so they stick together. So in this case, our equation doesn't work directly. Our equation that we derived assumes that this one is at rest. So what we want to do is then go to a reference frame where this one is at rest. So if I can go to a different frame where block 2 is initially at rest, and that means block 1 is going to be moving towards it. From that point of view, it's going to be moving towards it at a slightly faster rate. So we have to figure out what that speed is going to be. So we can do that. Let's write down here. So we know we want v2 initial to be 0. So v1 initial, we got v2 initial. What do we have to do to v2 initial to make it 0? Well, it's initially minus 0.447, so we added 0.447 to it. So that means we're going to add 0.447 to this one as well. So this one will be 0.352 plus 0.447 meters per second. And when we get that, add that together, we get 0.799 meters per second. And we have m1, right? m1 is 0.150 kilograms. We have that m2 is 0.100 kilograms. And we are trying to find the final speed v. So we'll find it in one reference frame, and then we'll switch back to the other reference frame. So our equation that we're going to use for this, our equation is, of course, m1 v1 initial equals m1 plus m2 v. That's a funny looking v. Let's do a better looking v. Okay, so solve that for v. It is just m1 v1 initial over m1 plus m2. And when I plug in all my values to that, I get 0.4794 meters per second. But I want v in the original frame, right? So v, the original frame, will be that v minus 0. Because we want to subtract that number we added before, 447 meters per second. And we get that the original v is going to be approximately 0.0324 meters per second, or if you want, 3.24 centimeters per second. So we're able to use our equation developed specifically for the situation where one is at rest by just switching to a reference frame where this one is at rest. It's a handy trick that you can use to solve these types of problems. Now we're going to look at the situation where it is an elastic collision. So the first thing we did was inelastic. That's where they stick together. Energy is not conserved in that case. But in here, let's assume it's a situation where no energy is lost. So, for example, if before the collision we have an object 1 with speed initial 1, and then we have object 2 with initial speed 2, and after the collision they've bounced off each other, they have the same mass, but they each have a different final velocity. So let's assume momentum is conserved. And most generally we have m1 v1 initial, so p total initial equals p total final. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. But we can't solve this by itself because we have two unknowns, right? If we only know the initial speeds, we don't know the final velocity of either of them. So if we include conservation of energy as well, i.e. we assume that the kinetic energy before is equal to the kinetic energy afterwards, we have another equation to work with. 1/2 mv, kinetic energy initial would be the kinetic energy of one plus kinetic energy of the other equals kinetic energy of that one plus kinetic energy of that afterwards. So these are the two kinetic energies after. These are the two kinetic energies initial. So now we have two equations and two unknowns. And we can combine these two to solve for V1 final and V2 final. We just want some equations that we can find the final velocity of these objects after the collision. Solving this is unpleasant. It involves a lot of algebra. We're not going to do it. You can do it if you want. If you want to have fun, you can figure it out. And you can get the final speed of object 1 and the final speed of object 2 in terms of the masses and the initial speeds. So you can get all the information, assuming that it's an elastic collision. And here's this big, wacky equation for each one. This is the most general one, and you can use it to solve it for elastic situations. We're going to look at some specific examples now for just the case where where V2 is at 0. It makes it a little bit easier. In fact, you can use this, and you can use the same situation we did before, where we just go to the reference frame where this one's at 0. But if V2 is 0, then that second term in each of those goes away, and V1 final only depends on V1 initial and the masses. V2 final only depends on V1 initial and the masses. And so this is handy. If it's an elastic collision, you can use these equations to solve certain types of problems quickly. So let's look at a situation where we have, we're going to look at some situations where block 2 is at rest. So if we have block 1 is approaching block 2, or sorry, ball 1 is approaching ball 2, and ball 1 has more mass than ball 2. What do you expect? We want to find the final speed of 1. Is it going to be moving to the right or moving to the left after it collides with ball 2? Well, let's look at the equation. What does your gut tell you? Think about what does your gut tell you. Well, this one's moving, this one's heavier than this one. Will it bounce off and move backwards, or will it keep moving to the right? Well, look, what does the equation tell you? It says that the final speed of 1 depends on the difference between 1 and 2. So if 1 weighs more than 2, then the number on top is going to be positive. So that means that this is claiming that ball 1 will be moving to the right afterwards because M1 is larger than M2. This is larger than this one. So let's hit play and see what happens. And you see that 2 is moving a lot faster than 1 afterwards, right? It has less mass in it and ends up gaining a lot of speed. So in the situation where M1 is greater than M2, they both end up moving to the right after the collision. How about the situation where M1 is equal to M2? Think about it, and then think about it in terms of the equation. Well, if we look at V1, what's the final speed of V1? What does this claim is going to happen if they have the same mass? Let's have a look. Look at that. In that situation, they have the exact same speed. Interesting. V2 is moving at the same speed, and the first one just stops. And that's what's claimed here, right? It claims that M1 minus M2 it's going to be 0, so V1 will be 0 after the collision. And if you look at V2, it'll just be 2m over 2m, and so V2 will actually be equal to V1. So all the momentum is transferred directly to the other one in that case. Now, how about the situation where M1 is less than M2? You can guess what's going to happen here. If M1 is less than M2, then this top number is going to be negative. And we get here, in this particular situation, M1 ends up bouncing backwards when it's bouncing off something that's larger. Let's do an example applying these new sexy elastic collision equations. Remember, these are only good for elastic collisions where the second object is initially at rest. So Here's a good calculation for something that often happens inside a nuclear reactor. One type of reactor uses graphite, solid carbon, to slow down neutrons. Turns out if neutrons are going too fast, that they're not good for nuclear fission. You need them at just the right speed. So sometimes you can use graphite to slow down those quick neutrons. So suppose a neutron, which has a mass of 1.67 times 10 to the minus 27 kilograms, is moving at 2.88 times 10 to the 5 meters per second, and it collides elastically with a stationary carbon nucleus, which has a mass of about 1.99 times 10 to the minus 26 kilograms. So the carbon nucleus has a much larger mass, right? Over 10 times more mass than the neutron. So it is much bigger. That means that we expect the neutron to bounce back quickly and the carbon to be moving more slowly afterwards. So find the velocity of the two particles afterwards. So here, everything here is written down. V1 initial, 2.88 times 10 to the 5, the mass of the one. V2 initial is 0, the mass is 1.99 times 10 to the minus 26 there. And afterwards, we want to find how fast they are going afterwards. So let's just write it all down again for yucks. We have M1 is 1.67 times 10 to the minus 27 kilograms. We have V1 initial is 2.88 times 10 to the 5, is it? Yes, meters per second. We have the mass 2, that's of the carbon nucleus, 1.99 times 10 to the minus 26 kilograms. And we want to find V2 final. We want to find how fast are they moving after the collision. And so we can do both of those using our two equations here. So let's find V1 final, right? That's just going to be M1 minus M2 over M1 plus M2 times V1 initial. So if I plug in all those numbers, I get minus 2.4 times 10 to the 5 meters per second. So as expected, the neutron is moving in the opposite direction. How about V2 final? Well, V2 final will be 2 times M2 using the equation, M1 plus M2 times V1 initial. How fast is it going afterwards? Well, 0.450 times 10 to the 5 meters per second. And so you notice, comparing this speed and this speed, right? The neutron is moving a lot faster to the left. The nucleus is moving, the carbon nucleus is moving to the right at a slowish speed. Here's another simple example. We have two balls on frictionless surfaces sliding around. So a 1 kilogram ball moving at 10 meters per second collides elastically with a 4 kilogram ball that's at rest. So we want to find out how fast are they moving afterwards. All right, so how fast is ball 1 and ball 2 moving afterwards? Well, we just used the two equations, right? So to find V1, we use this equation. So V1 final will be M1 minus M2 over M1 plus M2 times V1 initial, V1 initial, and we plug them in, we get about minus 6 meters per second. And for V2 final, it's just 2 times M2 over M1 plus M2 times V1 initial. And when we get that, we get plus 4 meters per second. So I'd like to do 3 more examples, sort of ranging all the different types of collisions we've looked at so far. So this is similar to one we did before. A 65 kilogram public defender is sitting on frictionless ice. She pushes a 125 gram stone away from herself, giving it a speed of 4 meters per second. How fast is she moving as a result? So before, they're both at rest, and then they end up moving, and we have the speed of the rock afterwards, and we can use everything to figure out the speed of her as well. So let's start by writing down everything we know. So let's see, for her we have M1, we have her 65.0 kilograms, we have her initial speed, it is 0, she's at rest, and we do not have her final, we want to find her final speed, right? So her final speed is what we're looking for. For the rock, well, or the stone, it's 0.125 kilograms, convert it to kilograms. The initial speed of the rock is 0, and the final speed of the rock is given as 4.00 meters per second. So we have everything we need here. It is not necessarily a, we're just given enough information here to figure it all out. So we can just do P initial equals P final. And P initial is 0 because, well, let's M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And we're trying to find V1 final. And we can say, well, this is 0 because they're both initially at rest. So 0 equals M1 V1 final plus M2 V2 final. So solve it for M1, move it over here, or solve it for V1 final, and that's going to be equal to minus V2 final times the ratio of M2 to M1. When we plug everything in, we get 0.00769 meters per second. That's not very fast, right? That's 7.69 millimeters per second. So that's how fast you'd be going at the end of that. This next example, we have a bullet flying towards a wooden block. So a 5-gram bullet moving at 650 meters per second hits a block at rest on a frictionless surface, and the bullet comes out through the other side. So the bullet basically tunnels through here and makes it through the other side, but it's lost on speed. It's traveling at 400 meters per second. So as a result of that, the block has started moving. Now, this is not a elastic collision. Energy is going to be lost into the deformation of the block throughout the whole thing. So we're just going to use conservation of energy and see if we can get a final answer for this. Well, let's start by writing down everything we know. Okay, so the mass of the bullet is 5 grams. So, you know, in kilograms, that would be very, very small. I think I have one too many zeros there. Get rid of that one. And then that is in kilograms. And then the initial speed of the bullet is 650 meters per second. The initial speed of the block is 0. What do we have? We have the mass of the block is 650 grams, so it's 0.650 kilograms. And we want to find how fast the block is moving after the collision with the bullet. And we do have the final speed of the bullet as well. It is 400 meters per second. So we have everything we need, and basically the equation we're going to use is P initial equals P final, right? The total momentum before is going to be the total momentum after. So it's M1 V1 initial, that's the bullet, plus the initial momentum of the block, M2 V2 initial. The block's initially at rest, that's going to be 0. And then at the end it's going to be M1 V1 final for the bullet plus M2 V2 final for the block. So we know, let's see, what do we know that's 0? Well, we know that this is 0 because the block is not moving initially, and we are trying to solve for the final speed of the block, because we here. So if I solve this, I can solve for V2 final. Okay, if I solve for V2 final, you can try this on your own. You can show that it is equal to M1 over M2 times V1 initial minus V1 final. I'll plug in some numbers here. So M1 is the mass of the bullet, 0.005. Well, let's not worry about sig figs quite yet. Divided by 0.650 kilograms times the initial speed minus the final speed, right? So 650 meters per second minus 400 meters per second. And when I plug everything in, I get that it's coming out at 1.92 meters per second. So after the bullet has gone through the block, the block is moving at about 2 meters per second. So the bullet transfers some energy to the block. Now, I said that we did not assume that this is elastic. So we assumed this is not elastic, right? And let's see if that's true. Let's see if it's not elastic. And one way to do that is to compare the kinetic energy, because if it was elastic, the kinetic energy before and after would be the same, right? So the kinetic energy initial would be the initial kinetic energy of the bullet plus the initial kinetic energy of the block, right? Which is 1/2 mv initial 1 squared plus, and the block is initially at rest. So when you calculate that for everything, you get approximately 1056 joules. And if I do the kinetic energy for afterwards, final, right, that would be the final kinetic energy of the bullet plus the final kinetic energy of the block. When I plug those numbers in, I get a much smaller number. I get 401 joules. So you see that energy was lost here. Energy got lost during this collision. So this is definitely not a an elastic collision. This example is to show you that it's easy to do this in 2 dimensions or with vectors. So I'd like to do an example with vectors real quick. So if you look here, it's 2 10-kilogram blocks collide. Before their collision, their velocity vectors are given like this: 30 I hat plus 60 j hat in meters per second, and for the other one it's minus 20 I hat plus 20 j hat meters per second. So if I want to draw for one, what does it look like? So this would be initial. So it's something like, approximately something like this, and for 2 it's something like this, I think, for 2, and then they collide. So it's, oh no, it's, the I hat is negative, right? So 2, it'll be something like this, and then they collide, and then afterwards, so that's before. After they collide, then you see here that V1 has this speed. So after the collision, V1 is this, and now we can find V2 at the end. So that part is easy. Let's do part A first. We're just going to do part A, and it's basically just that the initial momentum is equal to the final momentum. In other words, the momentum V1 initial plus the momentum of 2 initial is equal to the momentum, so this is, they both have the same mass, so I'm just using m, V1 final plus m V2 final, right? So we're trying to find V2 final, and you notice that all the m's cancel. It's kind of nice when all the masses are the same, so you're basically just adding velocities together. So solve for V2 final, and V2 final vector is going to be V1 initial vector plus V2 initial vector minus V1 final vector. So I'm just going to write it out. V1 initial is 30 I hat plus 60 j hat meters per second, and then to that we're adding V2 initial, which is minus 20 I hat plus 10 j hat meters per second, and then it's minus V1 final. Here's V1 final, right? So minus V1 final. I'm just gonna add the negative of that. So multiply that thing times minus 1, so it's plus 10 I hat minus 40 j hat meters per second. So now with this, I can add them together. So I'm going to add the 3 I hats, right? Plus 30 minus 20 plus 10. So I end up with 20 I hat. And then for adding all the j hats together, 60 plus 10 is 70, minus 40 is 30. So plus 30 j hat meters per second. So that's the final speed, or final velocity vector for after the collision. Now it asks for the change in kinetic energy. Now for the change in kinetic energy, it's a little bit trickier, because remember, kinetic energy is 1/2 mv squared in any given case. So v squared is the speed, right? We need the magnitude of each of those vectors. So I need the speed to calculate the change in kinetic energy for everything. So for example, the speed for V1, right, is going to be the magnitude of this V1 initial vector. It's going to be the square root of 30 squared for the I component plus 60 squared for the J component meters per second, right? And that works out, I'll keep extra sig figs for now, about 67.08 meters per second. So that's V1 initial. And I can do it for each of them, right? I have to add their components in quadrature. So V2 initial works out to about 22.36 meters per second. V1 final works out to about 41.23 meters per second. And V2 final works out to actually exactly 50 meters per second. So those are the final speeds of those things based on the vectors. And I can find, you know, for the initial situation, I can find the total kinetic energy initial, right? It'll be the kinetic energy of 1 initial plus the kinetic energy of 2 initial. So I do 1/2 mv squared for each of them, and that works out to approximately, for initial, 25,000 joules. And when I do it for final, K final, right, it would be K1 final plus K2 final. That works out to about 21,000 joules. So the change in kinetic energy will be the final kinetic energy minus the initial kinetic energy, and that works out to about 4,000 joules, or minus 4,000 joules. So this is, you know, not an elastic collision because the energy got lost during the collision. Okay, I'd like to do one last problem. This is a fun one, quote unquote. So we have 3 blocks on a frictionless surface. Block 1 has mass m, block 2 has mass 2m, block 3 has mass 3m. The first block has a speed of 10 meters per second. And so, you know, block collides with block 2, then block 2 collides with block 3, and it's asking what is the final speed of the whole thing after the 2 collisions. So after the first collision, so what do we have? We have that block 1 has collided and it's bounced back because it's smaller than block 2, right? And then block 2 is suddenly moving in this direction. We'll call it with speed V2. And then block 3 is still at rest after the first collision, right? So this is after the first collision. Now, what about after the second collision? So after the second collision, well, block 1 is still here, moving that way. That one's not really involved. But after the second collision, block 2 will have bounced off block 3, and it will be moving this way, right? This will be 2. And then block 3 will have collided, and it will be moving here. So we want to find the speed. This is what we're trying to find. We're trying to find how fast is 3 moving after that collision. So there's going to be 2 collisions in a row, and we can figure it all out. So let's do it for the first collision. So let's do the first collision. So for the first collision, let's write down m1 is just m, m2 is 2m. The velocity of 1 is 10 meters per second. And we just want to find the velocity of 2 after the collision, right? So that's V1 initial. We're going to find the velocity 2 after the collision. So I'm going to use the equation. So this here, important thing I meant to, and I will make sure that I will make this clear. If I tell you, you have to remember that in this case, I'm assuming that it is an elastic collision. If I don't tell you it's elastic, then you cannot make that assumption. But in this case, I'm telling you, you can make the assumption it's elastic collision. That makes it way easier. So that means we can use V2 final equals, this is those equations we developed for elastic collisions where one of the objects is at rest, right? So V1 initial. So if I plug in everything in here, it's 2 times m1, which is just m, and then m1 is m, m2 is 2 times m, and this is 10 meters per second. This ends up being 2m over 3m times 10 meters per second. You notice that the m's go away, and we end up with 20 thirds meters per second, which is about 6.66666. We'll go on forever, meters per second. Okay, so that is the block 2 speed, and we're going to use that for the second collision, right? So for the second collision, we have that block 2 has a mass of 2m, block 3 has a mass of 3m, block 2, in this case its initial speed is now its final speed from the last collision, so let's just put it as 20/3 meters per second. That comes directly from here because we're using that as the initial speed for the next collision. And we want to find the final speed for 3. And so here we're going to use the same equation as this, right? This one here. But we want to replace the 2's with, we want to replace M1s with M2s and the 2's with 3's because of the numbering. You got to be careful with the numbering. So V3 final will be 2 times M2 over M1 plus M2 times V2 initial. We plug in all our numbers, we get about 5.33 meters per second. All right, so after the two collisions happens, V3, this is moving at 5.33 meters per second. And we could also, if we want to, find out how fast these two blocks are moving in the opposite direction after those collisions.